Right, after some frankly abhorrent presenting in 5.1, let's see if we can make this one a little bit more smooth, fewer interruptions and less time me nipping off to find calculators and such like. So we're looking at Hess's Law, and this is kind of our basis of Hess's Law. This sketch sums it up nicely that if we're moving, come on pen, if we're moving along this way along a path, it's the same as if we were moving that way. Okay, as long as we start and finish in the same place, the overall energy change is going to be the same. So this is what we need to be doing by the end of this unit, and there'll be quite a few sort of simple calculations to look at. And you can have a read of this. This describes what Hess's law is, but this is probably the key bit down there, that the enthalpy change of a reaction is independent of the route taken, as long as you start and finish at the same place. And as a consequence that energy cannot be created or destroyed, the first law of thermodynamics. So let's say we've got this reaction here that we're interested in. Now you couldn't actually do this in the lab. If you take some carbon and you burn it and you say, right, I want to work out what the enthalpy change for this is, what's the energy change of burning carbon to forming carbon monoxide, you can't get just carbon monoxide. If you try and burn some carbon, most of it's going to go to carbon dioxide. You get a little bit of carbon monoxide, but you cannot just do this reaction. So if you wanted to work out what the enthalpy change was for this, you would have to make use of these bits of information. So these things can be done. We can get some carbon monoxide, oxidize it to CO2. We can take some carbon and oxidize it to CO2. So we can use this information to work out this mystery change. And there's two ways in which we can do it. Both are fine, whichever one you feel more comfortable with, but you need to really be able to understand the theory behind both. So this is our equation of interest across the top, and I've pinned around that the other changes that are happening. So here I've got my carbon reacting with oxygen to form CO2, which is this one, and that's minus 393. But you notice that minus 393 is per mole of this reaction happening. And looking at what I've got here, I need two lots of it. So as a result, it's 2 times minus 393. This one, it's as it stands. 2 COs go to 2 CO2s. There's my energy change. So my arrow's pointing. This is the direction of my reaction. So what I'm looking at saying is, using Hess's law, going that way is the same as going around there. So my delta H, my enthalpy change, which I'm trying to find out, is the same as 2 times that plus the opposite of that change. Now if I do the opposite of that, I have to change its sign. Because if, let's say, A going to B is minus 10, B going to A would be plus 10. Right? So if I do the opposite of the change, that becomes plus 566. And I solve that and I get the answer. Another way of doing it, very similar kind of logic, but without drawing out this triangle, is if I think, well, there's my target equation. What can I do to these so that when I add them together, I end up with that target equation? So if I multiply the top one by 2, this one here, because as we said earlier, I need 2 moles of carbon there. Done that, I've got to double the contribution in energy as well, so 786 there. This one, I need my CO as a product, so I'm going to flip that around. So again, you can think here, this is what you did here. You multiplied 1 by 2 and then you flipped. Multiplied 1 by 2 and then you flipped. So multiply that by 2 and I'm going to flip this one over, so it becomes plus 566 because I need CO as a product. And then when I add them together, everything cancels out except for my target equation. And when I add the equations, I add their delta H values, and there's my solution. So that's the one a little bit like what we've just been looking at. And there's the solution to it. You can work through these in your own time. And we talked about drawing these cycles. Whoops, do that just yet. But thinking of these arrows meaning which direction the reaction's taking place in, and remembering then how you're going to follow stuff through. Are you doing the opposite of that change and keeping that change? how does it change the signs when you use them in a calculation. Again, have a go at this. You can do one or both methods. This looks like the kind of manipulating equations to get to the target one method. If you wanted to do it the other way, let's see if we can draw out a Hess cycle for it so you can see what that looks like. So we've got S plus O2 goes to SO2 is what we're trying to find. And we've got information by which we've got SO2 going to SO3, and we're told that that's minus 98. And we've got information for sulfur going to SO3 as well, and that's minus 395. And I'd maybe need to be adding in an O on each of those just to balance it, but it's not critical, sort of just a bit of bookkeeping. Half O2, should we say? It doesn't matter. Either way, we're going to say that that is equal to going that way around. So we've got delta H is going to be minus 395 plus 98, and that's going to give us the answer. It should give us the same answer as, well, there. Right, lovely. Another example, again, a little bit more practice for you. Have a go at that. There's the solution. Make sure that you're pausing these and having a go at them. Another example. Oh. Okay, this is a little bit more complicated because you've got 4 extra reactions involved rather than just 2 others. But again, you can do it step by step, or you can do it by flipping equations, multiplying through equations, scaling equations, and then adding them, whichever way you feel most comfortable. So that's the flipping and adding. Let's see if we can do it the other way. Okay, so the information that we've got I2 forming 2I, and that's plus 151. I'm working with half that at the moment, so it's going to be a half of 151, and that's still got the half Cl2 with it. Then my Cl2s, if I want to make a change to those, I'll keep the 2. Oh. Right, we'll just have an I there because I've done half that. Then if I want to do the same for the Cls, then oh dear, I've made a bit of a blunder there. Let's start again. Okay. Right. Let's come this way to begin with. So I can get CO gas and I gas, and that's going to be plus 211 doing that. Now my iodine's currently a solid, and this is the mistake I just saw I made. I've got to get it to a gas first. So I'm going to change that from solid to gas, which is this one, but I'm only doing half a mole of it. So it's going to be half times 63, and that's going to give me I as a gas plus a half CO2. Half I2 gas, half Cl2 gas. Then I need to change this, atomize it, make the atoms. So I'm looking at this change here. So this is going to be half of 151. So that gives me I plus a half Cl2. And then my final change is to get that chlorine as atoms as well. And again, we're dealing with half of that, so it's going to be a half times 242. So, what a mess. But working around here, so I can say this change is equal to a half times 63 plus a half times 151 plus a half times 242 minus, going the opposite way, 211. Right, so I've built quite a complicated looking cycle. Or as I say, you can flip those equations around, same logic, and you end up in the same place with the same answer. Right, quick reminder of 2 definitions that we saw in the last session. Enthalpy of combustion, enthalpy change on completely combusting 1 mole of a substance with oxygen. Enthalpy of formation, forming 1 mole of a substance from its constituent elements in their standard states. And definitions are very important in this topic for understanding how to construct an equation and deciding what the equation needs to look like. So let's say in a question we've been given enthalpy of combustion data. So this is our target equation here. We're interested in finding the enthalpy change of that process. And we've been told these enthalpies of combustion. So I know the enthalpy of combustion of benzene, or whatever it is. Sorry, I can't quite read it. Hydrogen, and this compound here, butane. And what I can do is I can build those into a Hess cycle. So my enthalpy change, if I'm thinking of what a combustion is, my combustion is burning that to form combustion products. So I need to put in these enthalpies of combustions going down the way, like that, because that's what the definition is referring to. And then from what I saw with Hess's law, I can say that going this way is the same as going this way, and then the opposite of that arrow. So I can just use my sums there, and I can work out what my enthalpy change is. So here's an example. Maybe worth your while pausing me before I start to make a mess of it, and then you can see what I've done. So this is the reaction that we want. Enthalpy of combustion data, so we're burning this to form combustion product. I'm not going to spend time balancing it. You could write the word bananas here, it doesn't really matter. They're just products of combustion. The key thing is that you know that the arrow points down the way. So this is minus 715, and my CO being combusted is minus 283, and this substance being combusted is minus 876. And what I'm So, back again, going this way is going to be the same as going this way. So in other words, my enthalpy change is going to be going with the arrow 715 plus 283, opposite of this, so it becomes minus 876, and that's going to be my answer there. Right, formation data. Again, thinking what a definition for an enthalpy of formation looks like, it's forming 1 mole of a substance. So if we've got the enthalpy of formation of calcium carbonate here, forming 1 mole of that coming from these, then the arrow is going to be pointing up the way. Right? So there's an example, and this will be one that you can try. So again, pause me, have a go at this. Here comes the solution. So forming, again, we could write anything we want down here, but if we want to be absolutely correct, we've got hydrogens, we've got sodiums, we've got carbons, and we've got oxygens like that. Forming our sodium hydrogen carbonate, minus 948, but 2 moles of that. And then coming up this side, we've got sodium carbonate, which is minus 1131. We've got CO2, which is minus 3, and we've got water, 26. So putting that information together, going this way is the same as going around this way using Hess's law. So our enthalpy change is equal to the opposite of that, minus 2 times minus 948, plus minus 1131, plus minus 395, plus minus 286. And you can work that out. There we go. There's one more last worked example. Now if we're dealing with enthalpies of formation, just a small thing to mention as well, enthalpy of formation of something like this is going to be 0, right? If you think of the definition, forming 1 mole of a substance from its constituent elements in the standard state, well, oxygen as a gas is formed from oxygen as a gas, so the enthalpy change there is 0. That's what we've covered.